Okay, cool. So we are very happy to have Hofie Hannesdottir here from Harvard University here to tell us about the definition of a finite S-matrix. Thank you.
Yeah, thanks a lot, and thanks for the invitation to give this talk. So today I'm going to be talking about how to get a finite S-matrix, and this is work in collaboration with Chris Fry, Nisar Gopal, my advisor Matt Schwartz, Kayan, and more recently with Jake Bergelli, Andrew McLeod, and Christian Burgu. So the S-matrix is something that you've probably all seen. It's the probability amplitude, or should represent this probability amplitude for measuring some final state F, given some initial state I. And it's used in most quantum field theory calculations, and it leads to predictions for collider experiments. And in particular, standard model observables have been computed to high precision. And the way we usually calculate the S-matrix in perturbation theory is using Feynman diagrams. So since this is an object that is so widely used, its properties have been extensively studied. And people have tried to answer questions like, how do we encode the content of the S-matrix? Should we be using, say, spinors or twistors or the amplitude-hedron? And what are its symmetries? Does it obey Lorentz invariance, dual conformal invariance, or say the Steinman relations, which I'll talk a bit more about later. But despite all of this interest, the S-matrix does not formally exist in theories with massless particles. And the reason is that it's divergent in perturbation theory. And if we claim that the divergences exponentiate, then we also conclude that the S-matrix is actually zero non-perturbatively. So the questions that I am going to be discussing and addressing today are therefore the following. Why are our previous calculations valuable despite these problems? What's the fundamental object we should be calculating? And also, if we put things on a firmer mathematical ground, if we define something finite from the outset, what do we gain from that? Do we gain some insight, or do we gain some advantage? And yeah, so those are the points that I'm going to be discussing. So here's my outline. I'll start by elaborating more on what the S-matrix is and its traditional definition, which will lead to the reason why it doesn't exist in theories with massless particles, namely infrared or IR divergences. And then I'm going to go on to talk about ideas that we have for achieving IR finiteness. And then I'm going to go on to talk about one of these ideas, which is going to be to define a hard S-matrix, or SH. And this is an object that we define in our papers from last year, where we use universality of interactions in gauge theories to extract the interesting part and the non-trivial part of scattering amplitudes. And this object has at least 3 possible interpretations, which I'm going to talk about, namely as Wilson coefficients in soft-collinear effective theory, as remainder functions in n=4 super Young-Mills theory, or as coherent states. And in the end, I'm going to talk briefly about the new work. And we actually started looking into the analytic structure of amplitudes because we were interested in how it would help us in bootstrapping SH amplitudes. So in our most recent paper, we derived constraints or relations between discontinuities of amplitudes and cuts of the corresponding Feynman diagrams. So I'm going to talk briefly about that in the end. But let's start with the traditional definition of the S-matrix. And first ask the question, what is scattering? What do we mean by scattering, and what do we mean by the S-matrix? The traditional picture is the following. We start in the far past, when time goes to -infinity, with some state that's freely evolving. So this I here is an Heisenberg picture ket. So this combination here represents a freely evolving state in the far past. And then in some short time interval around, say, t=0, there is some scattering, which we represent with an evolution with a full Hamiltonian. And then we assume that in the far future, we again have a freely evolving state. And the S-matrix is again supposed to represent the probability amplitude for measuring some final state F given some initial state I. So let's look a bit further into this definition. Here is a cartoon that we like to draw. And the picture is as follows. We have our Heisenberg picture cats, which live at some reference time that I'm calling t equals 0. And then to get to the freely evolving state at time equals minus infinity, we have to evolve in the Heisenberg picture with the free Hamiltonian back here to minus infinity. And what happens then is that there's evolution with a full Hamiltonian up to plus infinity. And then to get back to our state f, which lives at time equals 0, we have to kind of evolve back again with a free Hamiltonian. So this is the operator that achieves this definition. It's the probability amplitude for measuring some final state f given some initial state I. And again, in perturbation theory in QFT, we calculate these S-matrix elements using Feynman diagrams. So let's do some...
Can we go back? Sorry.
Yeah.
So since we're trying to be general and define a quantity very generally, can you say how you would define H naught?
Yeah, so H naught here is the free Hamiltonian.
Yeah, but suppose I just give you a quantum field theory with some spectrum of particles. I'm not so interested in doing it just in perturbation theory. If we're trying to discuss when the S matrix exists, when it doesn't exist, etc., don't we need to answer it sort of more generally, what the ingredients are?
All of this construction is in perturbation theory, which is why it's clear in that case what we take to be the free Hamiltonian. So I'm assuming some Lagrangian description, and then I find my free Hamiltonian by removing the interaction terms. But
Is
you're
that
definitely
necessary?
right.
Is that necessary?
To remove the interaction terms?
No, for an S matrix to exist. Or I thought we were trying to figure out when the S matrix exists.
Mm-hmm. Maybe if I go on a little bit, that will answer your question. So what I'm doing here is just that I'm presenting what's traditionally done in the Lagrangian formalism in QFT, but it's a great question, and maybe I've alluded to it a little bit that we might want to modify this, as you say, in some theory where, say, we have massless particles. So let me get to that on the next slide, and definitely just ask again if it's not clear. Yeah, so if we use this definition, let's do some simple checks on it. Let's start with the free theory. What happens there is that the full Hamiltonian is the same as the free Hamiltonian. So S just becomes equal to 1, and the S matrix elements between two states F and I is just their overlap. And this is perfectly in line with what we expect, because if nothing happens, if we're just in the free theory, then the probability amplitude of getting some final state F given some initial state I will just be their overlap. Similarly, in quantum mechanics, when we have a short range potential, we also know from multiple examples that this definition works fine. But let's look at what happens if we have a constant potential. So if we take our Hamiltonian to be the free Hamiltonian plus some constant, and we just naively plug into this definition here, then our S matrix elements are the overlap of the two states, but then we also have this infinitely oscillating ill-defined phase here. And what we're doing wrong is clear in this simple example. What we're doing wrong is that we're assuming that the states evolve freely as time goes to plus or minus infinity. And that's obviously not a good assumption if I have a constant in my Hamiltonian, because there is no time when the constant turns off. It prevails at all times. So a similar thing actually happens in QED. So let's first look at what happens. Do we say that the S matrix is 1 minus alpha over epsilon squared, so that it's actually minus infinity? Or do we say that the divergences exponentiate, so the S matrix is actually 0? In either case, it doesn't help us. It's not well defined. It doesn't give us any non-trivial results. And the problem, again, is that interactions do not vanish as time goes to plus and minus infinity in QED. So there is no time when, say, the electron stops radiating photons. So using this definition, where we assume that things evolve freely at asymptotic times, leads to these problems in QED. Now let me elaborate a little bit on the problems before we go on. The problems is that these S-matrix calculations in perturbation theory sometimes give infinity. And this is obviously problematic because S-matrix elements squared should correspond to probabilities, and probabilities should always be less than 1. And we have two types of divergences. We have UV divergences, which occur at high energies. And we remedy these using renormalization, and that's very well known. But IR divergences, however, occur at low energies when we have massless particles. And we cannot use the same argument there. The argument that we use for UV divergences is that our theory in low energies should be independent of what happens at high energies. But these divergences occur at low energies. And in that case, we actually have no proof of the LSZ theorem, but we still use the S-matrix to make predictions. So one of the questions we wanted to ask again was, what can we gain from having a firmer theoretical foundation from the outset? So just to remind you briefly again before we go on about what kind of diagrams can lead to these divergences. Those are diagrams like this. I have an electron that radiates off a photon. And the propagator, if you take the numerator into account, will look roughly like 1 over the magnitude of the photon momentum k times 1 minus cosine of theta, where theta is the angle here between the two outgoing particles. So the singularities can occur both when the photon momentum goes to 0, which we call a soft singularity, or if actually both particles are massless here, we can have a singularity when the angle between the two goes to 0. And that's what we call a collinear divergence. And I'm going to be referring to either of these as an IR divergence.
Can I ask a quick question there?
Mm-hmm.
So can't you remedy this IR divergence by, say, resumming soft emission together with the virtual and soft photons inside of the loop, and that it can be made finite or independent of the IR cutoff that you introduce artificially to remedy the problem?
That's an excellent question and is precisely the content of my next slide and the next few slides actually.
Okay.
So perfect. Yes. Here are the ideas that we have for getting IR finite quantities. And the first one that I'm going to be talking about is precisely this idea, the cross-section method, which aims at getting IR finite cross-sections, that is S-matrix elements squared, integrated over some part of phase space, where we sum up over different processes in order to get an IR finite quantity. And we have some theorems that tell us how to proceed with this method, namely the Bloch-Nordzig theorem and the Kaelan theorem. So I'm going to go through both of those. Then I'm going to go on to talk about the new idea, which is to modify the S-matrix in a certain way, which leads to an IR finite S operator from the outset. So we don't need to square and integrate over final state phase space, we just have something finite for each matrix element. And then there's a third idea, which is to modify the states that we're scattering. So you might have heard about this as the coherent state method or the dress state method, and it aims at getting IR finite S matrix elements. But as we'll actually see as we go on, this 2 and 3 are mathematically the same. So they're a little bit different interpretations, but they correspond to precisely the same mathematical objects. So you can take either viewpoint and they're really two sides of the same coin. So let's start with discussing the cross-section method. The cross-section method is based on the following idea, namely that cross-sections are measurable and therefore cross-sections need to be finite. And perhaps if we have a detector and there is an electron in our detector, then maybe there was also a photon, but it just had such little energy that we didn't actually observe it, but it was still there. And all physical detectors have a finite energy resolution. So if our photon energy is just below that resolution, we won't detect it even though it was there. And then the idea is that if we sum over all such processes that are consistent with our detector measurement, then we should get a finite quantity. So this is the conventional solution to the IR divergence problem. And this is the solution that we started looking into when we first started this project. And part of the reason for that was just because it was the easiest framework, and we had these two theorems that told us how to start and how to proceed. So let's go through both the Bloch-Nortzig theorem and the KLN theorem. So the Bloch-Nortzig theorem is an old theorem in QED that says that soft IR divergences cancel when we sum over all final state photons with some finite energy resolution. And this is very physically appealing. This is just in line with the logic that I told you, namely that if we have a detector, then something might have been in our detector that we didn't see. And if we just sum over all possible final state photons, taking this detector resolution into account, then we get something finite. So this is great, works perfectly in QED. And it's actually interesting that right after this theorem came out, people thought that something similar had to hold in non-abelian theories like QCD because it's so physically motivated. But, whoops, Doria, Frankel, and Taylor actually showed in 1980 by an explicit counterexample that the Bloch-Nortzig theorem does not hold in QCD because QQ to mu mu QQ plus final state gluons is soft IR divergent at 2 loops. But this wasn't such a big problem in 1980. And part of the reason was that the KLN theorem had already been put forth in the 60s. And it says that S-matrix elements squared are IR finite when we sum over final states and initial states within some energy window. So what I have to do here is that I have to take into account that maybe I have an extra photon in my final state, but maybe there is also an extra photon in my initial state that I didn't measure because it was low energy or very close to the electron. And all I have to do now is that I have to take that into account too. I have to take into account both everything that could have happened in the initial state and in the final state. And then I should get something finite. So again, this is very physically appealing. And this is kind of where we started a few years ago. And we got a bit confused by simple examples. And we were asking the question, here it says sum over final states and initial states, but it's not really clear what those states are. So we were asking the questions, what's the minimal set of states that we need to sum over? Or what's the minimal set of Feynman diagrams that we need to sum over in order to get something IR finite? And again, we were confused about simple examples. So what we did in the end was that we went back to the proof of this theorem. And by studying the proof, we realized that we could actually prove a stronger version of the KLN theorem, which says that S-matrix elements squared are IR finite when we sum over final states or initial states. So I've done two things here. I've both eliminated the need to sum over both final states and initial states. And I've also gotten rid of this energy window. And if you think about it a little bit, this energy window kind of doesn't make sense because the S-matrix elements, the S-matrix conserves energy. So the cancellation of IR divergences has to happen point by point in energy phase space. But so you might now ask, how is this consistent with Doria, Frankel, and Taylor? I just told you that you couldn't just sum over final state gluons. But notice that there's a difference here. And the difference is that in Bloch-Nortzig, you want to sum over final state photons, which in QCD would be to sum over all final state gluons. So this is what they calculated, QQ to mu mu QQ plus all final state gluons. But in the KLN theorem, we have to sum over all final states. So we can fix our initial state to be QQ, but in order to get a cancellation, in order to be guaranteed to get a cancellation of the IR divergences, we also have to sum over the process where QQ goes to QQ. So we have to sum over the process where nothing happens. And if you look at this equation and stare at it for a little bit and listen to that logic that I'm telling you, then maybe you realize that what I'm telling you is actually entirely trivial. And the reason is that if I expand this out, I get a complete set, I get a sum over a complete set of final states here, which just collapses to 1. And the S matrix is unitary, so S dagger S is also just 1. So this whole sum that I had in the KLN theorem is actually just equal to the overlap of the initial state with itself, which in some normalization is 1. And 1 is less than infinity. So what we conclude from this is that the KLN theorem is actually just equivalent to unitarity. And if we sum over all possible diagrams and anything that could have happened, then we get 1 by unitarity. We just get that all its probabilities sum up to 100%. And 1 is IR finite. So using the KLN theorem, we're actually not closer to finding the minimal set of diagrams that's needed for IR finiteness.
I'm sorry, can I ask a quick question?
Absolutely.
So I would have thought that the original question was that given a hard process, I wanted to cure the problem of IR divergences by attaching IR soft radiations.
Exactly.
But then if you had to add also QQ, for example, in the case of a QCD example, you seem to adding another hard process on top of the harder processes that you were interested in originally.
Exactly.
So how is it actually solving the original problem of IR divergences of the?
It's not at all.
Oh.
That's precisely the point. It's not helping us. We're not any closer to finding this minimal set of diagrams. So this is where as I say, it's important here also that the KLN theorem from the 60s, it's a weaker version of what we proved. I mean, the reason why we were getting confused is because we weren't including everything. And sometimes you need the forward scattering contribution. As I say, here you need QQ to QQ in order to get this cancellation. And then if you say, okay, the only thing that the theorem tells me is that all the probabilities sum up to 1, then you're just back to unitarity. And
right.
it doesn't help you. It doesn't tell you anything non-trivial.
Right.
So this is where we decided to look into modifying the S matrix.
Oh, okay. Sorry. Yeah. Okay. Thanks.
So yeah, again, great question. And what I will address in the next few slides.
Can I ask a question?
Mm-hmm.
Sorry. Yeah. So I thought for, obviously you're saying all inclusive, this doesn't do anything, right? So that then I thought even for exclusive final states, right? So we have all gotten used to, finding infrared safe observables to calculate.
Yeah. The point here is basically that, I guess the main point is that sometimes what you think is IRC safe is actually not. Like, for example, this business of summing over all initial states and final states within some energy window, although it sounds physically appealing, it's not the correct thing to do. But precisely like you said,
for each case, we learned whether something is IRC safe or not, right? So
exactly.
But that's there's no problem with that, right?
There's no problem.
Learn that we shouldn't ask infrared unsafe questions.
Exactly, and like for most collider observables, they have been proven to be IRC safe, say, and also I should say for many processes, it's known which diagrams to sum over in a case-by-case basis. But as I say, what we wanted to point out is that you get that insight from things like factorization, and the KLN theorem doesn't tell you, again, what's the minimal set to sum over. But we definitely have other ways of knowing that, and that's precisely what we're going to be using going forward when redefining the S matrix. We're going to be using that to our advantage, that we actually know a lot about factorization and about which processes to sum over and get something IR finite.
Okay.
So yeah, let's talk about that. Let's talk about the next method, which is to modify the S matrix to SH. So recall that we talked about earlier that as time goes to plus and minus infinity in QED, interactions do not vanish and they don't turn off at some point. So it's natural in these theories to redefine what we mean by the S matrix, to not assume that our states evolve freely at asymptotic time, but rather assume that they evolve with some modified asymptotic Hamiltonian that takes these long-range interactions into account. So the cartoon we have now is that instead of starting with an initial state ket that evolves freely back to minus infinity, we can actually have something non-trivial happening here in the evolution from time equals 0 to time equals minus infinity. And then we have evolution with the full Hamiltonian to plus infinity. And then when getting to the final state ket, we can again have some non-trivial asymptotic evolution. So if we accept that this is, or this may be a sensible thing to do, then that immediately raises some questions. First of all, how do we pick this asymptotic Hamiltonian? There is some criteria. First of all, we want the hard S matrix elements to be IR finite, but we should also note that that's not restrictive enough, because if that was my only criteria, then I could pick H asymptotic to be the same as H. So S would just be equal to 1, and all S matrix elements would just be the overlap of the two states, and everything would be trivial and wouldn't tell us anything interesting. So we definitely want it to be IR finite, but that's not restrictive enough. We also want it to be calculable, preferably easy to calculate, but we want it to be useful. We want it to correspond to a useful quantity and not just something trivial. But then it also has to be consistent with all the measurements that we've made so far. As we've discussed, we can't say that everything is going wrong because we've calculated many observables for colliders, and we know that our theory agrees very well with experiment. So we can't say, oh, let's start from the beginning and say that everything that has been done so far is wrong. But if we find some sensible thing to pick for H asymptotic, then that also raises the question of how we calculate these matrix elements of SH and how we interpret them. What do they correspond to? So let me go through these questions one by one. First, how do we pick the asymptotic Hamiltonian? The choice that we're advocating for in our papers from last year is to use factorization to our advantage and techniques that have already been developed in soft-collinear effective theory, or SCT. So for those of you who are not familiar with SCT, it's a low energy effective theory for the Standard Model, which is used a lot to predict quantities for colliders. And it includes the soft and collinear degrees of freedom of the theory. And by factorization theorems in SCT, we know that this choice of H asymptotic will give us IR finite S matrix elements. And this is possible because of the universality of IR divergences in gauge theories and factorization theorems in SCT. And what this operator achieves is that the states will evolve independently of how they scatter. So we're kind of stripping off the IR divergent universal part with this choice, and we're left with the non-IR divergent and non-trivial part. And we will generate new UV divergences with this construction, and that's already known from SCT, and we deal with that using renormalization as usual. And another upshot of this method is that we don't introduce any new scales in this construction. So a lot of our integrals actually end up being 0. And we also tried in our paper, I should say that, we tried putting in scales and seeing that the construction worked out by not setting everything to 0, but I'm going to show you this trick later because it gives the right answer without a lot of calculations. So the second question is, how do we calculate these matrix elements? And this is actually general, not only for the SCT Hamiltonian as the asymptotic Hamiltonian, but what we did was that we just derived the Feynman rules for this type of construction. And what ends up happening is that you can use this trick in perturbation theory where you insert a complete set of states twice, which I'm calling I prime and F prime here. And then your calculation splits into 3 parts. So again, this is just a trick that I use, and I'll have a central region, which is just the usual S matrix element between F prime and I prime. But then I also have these outer regions where I have to use time order perturbation theory rules. And then I have to sum over all possibilities of I primes and F primes over here. So let's do an example to see how this works out. I'm doing the example of a Z boson splitting into an E plus E minus pair. And I'm taking the asymptotic Hamiltonian to be the SCT Hamiltonian. So here is my Z. I'm denoting it with a dashed line to distinguish it from the photon, which is a curving line. And what I have to do is that I have to fix the state on the far left and far right here. So the first diagram I can draw is just the usual virtual loop here. And if you remember, the middle region here just uses usual Feynman rules. So this is just precisely the same as we usually calculate. And we can do this calculation, and it's UV and I are divergent, and then we also have some finite part here. But then in this construction, we also have to add the possibility of a photon being emitted and absorbed in the asymptotic region. And similarly, we have to add the possibility of a photon exchange in the asymptotic region. So we have to include all of these interactions in the asymptotic region and then draw all diagrams that are consistent with that. And now there are two ways to calculate it. We could either use the Feynman rules that we derived, or I told you about on the page before, where we use time-ordered perturbation theory rules here in the asymptotic region, or we can use this trick. And I'm going to show you the trick here on these slides. And the trick is to note that the IR divergences of these three diagrams have to cancel with the IR divergence up here, because we know that this combination of all these four diagrams can't be IR divergent. So I can immediately write down the IR divergent contribution. It will just be this term here with a plus sign out front. But then I also know that there are no new scales in my construction. So actually these three diagrams have to also add up to 0. So now I actually know my answer, and this is my answer. If I take epsilon IR to be equal to epsilon UV, you see that this whole thing becomes 0. But the reason I could write it down right away is because I know that these IR divergences here have to be equal and opposite to these ones up here. So the total result, the hard S matrix element for this process, Z going to E plus E minus, if I renormalize in MS bar, so I drop all the UV divergences, it's just a finite part of what I started with. And if you're familiar with SCET, you might recognize this calculation. It's precisely the calculation of the Wilson coefficient in SCET. So that brings me to the first possible interpretation of these hard S matrix elements. Namely, they can be interpreted as Wilson coefficients in soft-collinear effective theory. But as I'll show you in a couple of slides, they can also be interpreted as remainder functions in n equals 4 super Yang-Mills theory, or as dress states or coherent states. So let's go briefly through these one by one. As I told you, this is a familiar expression and a familiar calculation to those of you who have worked in SCET. So the SH amplitudes are actually the same as the Wilson coefficients in SCET, which are the coupling constants in the effective field theory. And what these...
I'm kind of lost. I think it's mostly because I don't work on SCET, but I think that's true of many people in the audience. So yeah. Is SCET usual quantum field theory?
Yeah. So
it's a fully Lorentz invariant local quantum field theory?
Exactly. So it has these, the degrees of freedom are basically just like the soft limits and the collinear limits of full QCD, but then you don't put any scales in. So as I say, the reason why, if you work in DIMREG for both your UV and your IR divergences, then your integrals.
The question of which regulator we're working in shouldn't matter for the answers to these questions.
Exactly. So, I mean, that's super important too. And as I say, we have checks of that in our paper. So this is just a very neat trick that you can use if you want, but you can also say, put in a different IR regulator, and then you see the cancellation too.
So if we're discussing QED, what is the SCET Hamiltonian for that theory?
So the SCET Hamiltonian would be, again, it would have the soft fields in that case.
What is the soft field? Is it a scalar? What does it depend? I mean, I think I know what some elementary quantum field theories look like. You said it was a normal quantum field theory. Can you describe it in that language?
What do you mean exactly?
Well, I'm confused about what are the degrees of freedom in SCET. Are they some fields with usual spins?
Exactly. So I guess Yeah. The way I think about it, as I say, is that take your usual QED or QCD fields, and then you basically power expand so that you only keep the soft part or the collinear part, and these are distinct. So you actually have some double counting of the overlap of soft and collinear.
But does collinear mean that the final Hamiltonian is not Lorentz invariant because I'm expanding about some direction?
It's still Lorentz invariant. Why would it not be?
Well, collinear sounds like you chose a line. I just don't know much about this. So,
Clay, Lorentz invariance is restored by reparameterization invariance.
So then, can we just say what the sket Lagrangian is for QED? If there's a Lagrangian, can we just say what the fields are?
Absolutely.
Yeah.
Let me.
Clay, it's easiest to think about it in momentum space. You're getting rid of high energy modes and as Hofie said, keeping.
But I mean, if it's just a regular quantum field theory, can't we just expand it in some fields and see what we're talking about?
Yeah. So I mean, all of this is of course based on like starting with again QED or QCD and expanding in these limits, and then that's the Lagrangian that you get. So I can show you, we have in our
maybe
paper.
I don't want to derail you too much. Maybe we can.
Yeah, maybe we can discuss this afterwards. But
Sure.
Here, if you can see my screen, this is from our paper. This is just the sket Lagrangian where you've expanded your fields in the soft and collinear limits. So the psi n's here are the collinear fields. And yeah, these are the soft fields for the gluons and the collinear fields for the
So it
gluons.
has derivatives in the denominator.
Mm-hmm.
Doesn't look very local. But anyway, maybe we'll talk about it afterwards.
Yeah, sounds good. Okay. So yeah, what I wanted to point out here is that now that we have this new definition of Wilson coefficient, that's really different from what we usually do, because usually we take the difference of matrix elements in the full theory and the effective theory. And these matrix elements have different fields and different quantum numbers and different degrees of freedom. But here we take matrix elements of a single operator where we use the same fields, but different Hamiltonians. So when we have this new definition, we can ask questions like, what are the analytic and symmetry properties of the hard S matrix? And what can we learn from bootstrapping the hard S matrix, which I'll get to a little bit in the end. And then I want to briefly talk about the relation to remainder functions in n equals 4. So n equals 4 super Yang-Mills theory is a toy model which obeys supersymmetry and dual conformal invariance. And dual conformal invariance means that the amplitudes only depend on ratios of Mandelstams that are dual conformally invariant. And amplitudes in this theory have recently been bootstrapped to 6 and 7 loops using some constraints that I'm gonna talk about later, like the Steinmer relations.
Wait, sorry, but in n equals 4, aren't the issues more severe at finite coupling than the kind of issues you're talking about? Because then all the correlation functions would just have some branch cuts. It wouldn't just be an issue of having some finite set of massless particles and then a gapped spectrum, right? Like that's a real interacting CFT. Are you saying that you can define an S matrix in an interacting CFT as well?
Let's talk about that after the talk. I've had a few discussions about that with people. I'm not really sure, but I wanted to point out here that if you calculate S matrix elements in n equals 4, then the IR divergences actually obscure the symmetries and simplicity because dual conformal invariance is violated at one loop. And instead, people compute remainder functions that are ratios of the full amplitude and an exponentiation of the one loop divergences. So this is how people use the universality. They exponentiate the one loop divergences and then calculate the remainder functions. And the remainder functions sometimes obey some constraints like the Steinmer relations, or dual conformal invariance, which can help with bootstrapping. So I want to flash at you what the one loop amplitude, the 4.1 loop amplitude looks like in n equals 4. And as you can see, this is not a simple expression at all. It's not dual conformally invariant. But what we can do is that we can use the universality of IR divergences to simplify this. And that's something people have already done, as I say, by computing remainder functions, which compute basically the ratio of amplitudes to an exponentiation of this one loop amplitude, which has all the full IR divergences here. But the approach using the hard S matrix is to subtract divergent amplitudes instead of taking ratios. And what happens then is that you get this very simple answer after renormalizing. You get that the for loop amplitude, the hard amplitude, the hat here is supposed to denote the hard amplitude, is just given by this simple expression, which is very different from the slide I showed you earlier, which has a much more complicated expression. And we can also see that the two loop amplitude exponentiates, the two loop hard amplitude exponentiates in terms of the one loop amplitude. So what I wanted to point out here is that factorization and techniques from soft-collinear effective theory actually explain why these remainder functions take a simple form. And the reason is that the IR divergences are universal.
Sorry, can you say what it is that you're computing in the standard language of n equals 4?
Yeah, the remainder functions, absolutely. So the remainder function.
I have a list of local operators, scaling dimensions, OP coefficients. What is it that you're computing?
So this is using, again, the Lagrangian formalism. So
that's fine, but in the end, all that
diagrams.
stuff is just a machine for computing those intrinsic observables of the conformal field theory.
Mm-hmm. So a remainder function, then you take the full amplitude to some order in perturbation theory, and you divide it by an exponentiation of the one loop divergences. And then you compute this ratio, and this ratio is finite.
Yeah, I don't think you can frame this claim in the language of CFT observables, like some correlation functions.
But that's why I'm confused about whether it really exists as like a non-perturbative object.
Yeah, I think it's meant to be sort of in the close to free limit where you're scattering gluons and pretending that.
But at any small but non-zero coupling, that's just not a good picture, even no matter how small the coupling is.
Yeah, the interactions don't shut off. That's right.
And it's not even that they don't shut off, but because there's some free particle, free gluon.
Right.
What do you mean by that?
What I mean is that there's non-zero anomalous dimensions. Like, in other words, if you look at the correlation function of like, imagine we look at the 2-point function of the field strength operator, some gauge invariant observable. Now F is good. It may, in QED, F has some amplitude to make a photon.
Mm-hmm.
But in QCD, the 2-point function of F, if you like did a Kalin-Lehman representation of it, it wouldn't even have a pole at 0. Just have some branch cut going down to 0, some continuum going down to 0. So it looks like qualitatively quite different to me.
Yeah, I see. Let's definitely discuss this more, as I say, because I've had a few discussions about this, but I'm very interested to hear what you think. But yeah, let me finish in the last part of this, talking briefly about coherent states. So the main point that I wanted to tell you about coherent states, which you may or may not be familiar with, it's the coherent states I'm referring to here are the same as the Faddeev and Coolidge coherent states, or the Chang coherent states. And what happens is that these arise as the mathematical objects that are the intermediate steps in this calculations of the hard S matrix. So if you remember this picture here that we looked into, the state here at time equals plus infinity is a dressed final state. And in the coherent state picture, we say that this linear combination of states is actually the states that we're scattering at time equals infinity in the Schrödinger picture. So I just wanted to point out that this is the same mathematical construction, but the problem with the coherent states is that these are IR divergent states themselves. So instead of having an IR divergent S matrix, we have IR divergent states instead. So Yeah, I'm not sure if that construction is helpful or not.
So I just want to make sure I understand. So the states I prime, these are meant to be the Coolidge-Vateov dress states, or
no, that's ID here.
That's multiplied by that. Okay.
Yeah. So the coherent states are this whole object here.
So that fully that's the fully dressed.
Exactly, and they arise, as I say, we use this three-part construction. We insert these I primes and F primes, basically so that the calculations are easier. There is nothing else that tells us to start summing over states. It's just if we start with the hard S matrix operator here, we wouldn't know how to start calculating anything. So in order to kind of get back to the Feynman diagrams and the things that we are able to calculate in perturbation theory, we insert these states. But it's still interesting that mathematically they correspond to exactly the same objects as, say, Faddeev and Coolidge. So and which is then this whole thing, this whole bracket.
So I thought the claim, which I don't understand properly, that I thought there's a claim that asymptotic symmetries force you to consider these combinations of states rather than F and I.
Right, so that's something that we've looked into, and I'm actually working with one of Andy Strominger's students in exploring that. And the claim there is that, so what they've shown is that all S matrix elements conserve this asymptotic charge. And if you scatter eigenstates of this asymptotic charge, those are the same as the Faddeev and Coolidge states. But the question that is still outstanding is why is the right thing to do to scatter eigenstates of this new asymptotic charge? And that we're not sure of anymore. Because if you use the argument that it's conserved, then we could as well ask, why don't we then scatter momentum eigenstates? Because momentum is also conserved, right? So those would be plane waves, and that gives something IR divergent. So there's...
Could I just, a quick question on that. So the asymptotic charge is a super selection sector of the theory. So is that a very good reason?
To
consider eigenstates of the asymptotic charge as opposed to eigenstates of some, other conserved quantity? Yeah,
so as I say, to me, that's still an outstanding question. Why or if that's the right thing to do. But the claim is that eigenstates of this asymptotic charge are the same as the Faddeev and Coolidge coherent states. And we know that scattering them gives an IR finite quantity, basically based on the Faddeev and Coolidge paper. Or now we know also based on factorization theorems. And yeah.
But sorry, is part of your point that these Faddeev-Coolidge states are sort of formal? They're not really states in any Hilbert space once you remove the regulators? Like
that's one of the points.
Is this ID infrared divergent once you take into account
yes, yes, exactly. So what I want to point out here, as I say, I don't want to diminish other people's work or say that this is this won't be fruitful, because we're still working on it, and I think it's an interesting direction for this project. But I think there are still outstanding questions, like, for example, these states are divergent. They're not part of any well-defined Hilbert space, so it's unclear how to resolve those questions. But the main point I wanted to point out is that it's the same construction as the hard S matrix, and they can also be found by this construction of modifying the asymptotic interactions. So that's the main point I wanted to make. It's kind of two sides of the same coin, and it really corresponds to whether you want to look at the Heisenberg picture or the Schrodinger picture, because these states live at time equals plus infinity or time equals minus infinity. So then you kind of force yourself to be in the Schrodinger picture.
And just to make sure I understand what ID is supposed to be, if I go to parametric, if I go to zero coupling, is ID, and I'm in like a position basis, is ID an electron dressed at long distances by its Coulomb field?
Exactly. So maybe this picture clarifies it. So
okay, I see that there's lots of photons, but I don't see that they add up to the Coulomb field. That's what I was trying to make sure I understand.
Yeah, so it should be basically the inverse of the Coulomb field that cancels the IR divergences. You kind of strip off the Coulomb field is how I do
Using
it.
coherent state to demonstrate IR divergence cancel, that has been done a long time ago.
Absolutely. And this is why this is interesting. And as I say, now we also have more information than when
But nobody
Fedeli
has
and Coolidge
succeeded
was
to do it for non-Billiard gauge theory.
Exactly. We don't have a coherent state construction like this in QCD or non-abelian theories.
So you are not claiming that you have one, right? So just to make sure.
Yeah.
Well,
so
why can't they just use the Sket Hamiltonian in there to define what they mean by ID for QCD?
You can, but it's a little bit different from the goal of these coherent states, because it basically boils down to where you have non-factorization, and we can include that in our asymptotic Hamiltonian. It's called Glauber operators, if you've heard of those. But yeah, you can't really, there you have to include it in your Hamiltonian. You can't really sum over these states because those become potential-like operators, basically. You can't just like sum over gluons in order to get coherent states in QCD.
I mean, the whole thing is still based on factorization. You have to.
Absolutely.
Glauber gluons break the factorizations.
Exactly.
I have another point of clarification. So in the usual Fedeli-Coolidge, like with massive particles, they dress with some I guess infrared divergent electromagnetic state. If you have massless particles, in your way and what you're doing, are you requiring? I mean, you have now two massless fields in the game. The massless, electrons. Are you requiring that they're infrared finite?
Yeah. So this was actually one of the original reasons why we started looking into this. It was to also cancel, like, what's the construction for also canceling collinear divergences? And these divergences are either 1 over epsilons if you take the electron to be massless, or they look like log of the electron mass over the hard scale in your problem if the electron has a mass. So it can still be a big quantity if you take your hard scattering scale to be large. If your center of mass energy, say, is large compared to the mass of the electron, then you'll get these large logarithms. So we also wanted to cancel those.
Are these collinear divergences the same as like a divergence in the number of particles? Or is that I'm confused at what these collinear divergences are.
There, as I say, they come about just because imagine an electron at rest that has just like radiation around it, and then you boost it, and then all the radiation becomes collinear. And that's where the divergences come from.
Oh, I see. It's like, oh, I see. Okay, thank you.
Yeah, you're welcome. Okay, I guess we're almost out of time because of many great questions. Let me mention extremely briefly the new work that we've been doing. So as I told you, we have this alternative definition of familiar objects. And what we were interested in was to use, for example, bootstrapping methods and constraints to examine the properties of the hard S matrix. And we realized that we needed a better handle on the analytic structure of amplitudes. So we started looking into generalizing the cutting rules. So the usual cutting rules relate discontinuities of amplitudes to cuts of the corresponding Feynman diagrams. And the game is then that you can do the cut computation, which is often easier than computing the full amplitude. If you do the cut computation and sum over all cuts, then you know the discontinuity of the amplitude. And then you can often reconstruct the full amplitude using information about its discontinuities if you have, say, a basis of functions for your Feynman integrals or some other constraints. So what we were looking into was what we can learn from taking more discontinuities, so discontinuities of the discontinuity, and what happens in different kinematic regions, that is for different signs of the Mendel stems, and how we relate those discontinuities of discontinuities to cuts of the corresponding Feynman diagrams. And these are the results from our most recent paper. First of all, we realized when starting to address these questions that we needed more precise mathematical tools in order to compute these discontinuities in different kinematic regions. And the reason is that if we define the discontinuity of the amplitude as the difference between the amplitude with all plus I epsilon and the amplitude with all minus I epsilon, so we're computing the difference across the branch cut, then that function just lives on the branch cut. It's not a function in the full complex plane. So we actually had to redefine what we mean by discontinuities. And the way to do that is to use monodromies. So we analytically continue the function, not just in the complex plane, but we find these discontinuities by doing analytic continuation around singularities. And then we related these sequential discontinuities to multiple cuts through the corresponding Feynman diagrams. And we also had a new proof of the Steinman relations, which I mentioned a few times in this talk, and are basically constraints on amplitudes that forbid sequential discontinuities in overlapping momentum channels. So let me skip, if any of you are interested in this, I'm more than happy to discuss it more, but let me skip through these slides since we're out of time and go to my conclusions. So we've discussed the hard S-matrix definition, which we define by exploiting the universality of asymptotic interactions in theories with massless particles. And this hard S-matrix encodes the hard dynamics of the scattering process and has three possible interpretations that we know of, namely as Wilson coefficients, as remainder functions in n equals 4, or as coherent states. And as a future direction, we wanted to look into the analytic structure of the SH amplitudes, but we actually realized that we first needed to look into the analytic structure of S, where we have more known results, and we started probing these, this analytic structure by using our new relations between sequential discontinuities of amplitudes and multiple cuts through the corresponding Feynman diagram. So thanks everyone so much for coming and for the great questions so far. And I'm happy to discuss all of these points more.
Okay, I think maybe now we should take a quick 5-minute break. People can use the restroom or get some coffee, and then we can have some more group discussion and ask our questions and such. So I'm gonna leave this channel open, but I'm gonna turn off my video and mute, and I'll see you guys in a few minutes.
Sounds good.